All right, so we're going to continue with our natural log differentiation. Just like what we were doing yesterday where we had to use the properties of logarithms, I could either differentiate this and have it be really, really messy, or I could use my properties of logarithms to separate this out into smaller chunks and then differentiate those smaller chunks. So using the properties of logarithms, whenever I multiply, I know that means I have to add, so I'll have the natural log of x plus, and then because this is the exponent, I'll bring that down front. So I have 2 natural log of x squared plus 1, and then because this is in the denominator, I know I'm going to subtract, and then because this is the square root, I know that has a 1/2 power of the natural log of 2x cubed minus 1. So now we just have to differentiate this problem, which is easier. So we learned yesterday that the natural log of x would just be 1 over x plus the natural log of x squared plus 1. So I have 2 times 1 over x squared plus 1. And then I have to take this times the derivative of the argument, which is 2x, minus 1/2 times the derivative of the natural log of 2x cubed minus 1 would be 1 over 2x cubed minus 1. And then I have to take this times the derivative of the argument, which would give me 6x squared. Now I just have to simplify. So I'll leave this as 1 over x. And then here I would wind up with 4x over x squared plus 1. And then here I can take half of 6. That's where I'm getting the 3x squared from, over 2x cubed minus 1. Now if you want to, you can get a common denominator, but I am perfectly fine leaving this as your final answer. For our next problem, I'm going to do the same type of thing where since they don't have a log in the problem, I'm going to go ahead and take the natural log of both sides so I can simplify this problem. So I'd have the natural log of y equals 2 times the natural log of x minus 2 minus 1/2 times the natural log of x squared plus 1. Because now when I find the derivative, I know the derivative of the natural log of y would be 1 over y dy dx equals 2 times 1 over x minus 2 times the derivative of the argument, which is 1, minus 1/2 times the derivative of natural log of x squared plus 1 is 1 over x squared plus 1 times the derivative of the argument would be 2x. So now if I simplify this, this would be 1 over y times dy dx equals 2 over x minus 2 minus half of 2 would give me x over x squared plus 1. Now when I'm finding the derivative, remember that dy dx is a form of the derivative, so I just want dy dx here. So to get rid of this 1 over y, I will multiply both sides by y. So I'll get dy dx equals 2 over x minus 2 minus x over x squared plus 1. And I take this quantity times y, which if I go back up to my original problem was x minus 2 squared over the square root of x squared plus 1. By taking the natural log of both sides, I was able to find easier, smaller derivatives instead of having to do a quotient rule and the chain rule in the process of having to do the derivative in the first place. And I'm perfectly fine if you want to leave your answer this way, or you could get a common denominator and multiply this out. It's your choice. Right, so because the natural logarithm is undefined for negative numbers, you will often encounter expressions of the form the natural log of the absolute value of u. So So the following theorem states that you can differentiate functions of the form y equals the natural log of the absolute value of u as if the absolute value sign were not present. So that's all what they're saying here in this, is that basically they're just putting that absolute value in there so we know that we can go ahead and treat it like a normal function because we can't take the natural log of negatives. They're just taking away the negatives by putting the absolute value in there. But it doesn't affect how we actually take the derivative. So for example 7, we want to find the derivative of f of x equals the natural log of the absolute value of the cosine of x. So I know the derivative of, I'm just going to pretend like these absolute value bars aren't even here and not worry about them. So when I take the derivative, I'm doing the derivative of natural log, I know would be 1 over the cosine of x. And then I take this times the derivative of the argument of cosine of x, and that gives me negative sine of x. So I know this would be negative sine of x over cosine of x. And using my trig identities, I know this is the same thing as the tangent of x. So I have negative tangent of x. So then for example 8, we want to find the relative extrema of this function. Remember, relative extrema is our maxes and our mins. And in order to find the maxes and our mins, I want to figure out where the function changes from increasing to decreasing or decreasing to increasing. So to do that, I need to find the derivative of this so I can find out where my critical numbers are. So my derivative of the natural log of x squared plus 2x plus 3 would be 1 over x squared plus 2x plus 3 times the derivative of the argument, which would be 2x plus 2. So essentially, I have 2x plus 2 over x squared plus 2x plus 3. So to find my critical numbers, this is where I need to find out where is y prime equal to 0 and where is y prime undefined. So y prime is equal to 0 when 2x plus 2 equals 0. So I'll subtract 2, divide by 2, and get x equals negative 1. And then where it's undefined would be where x squared plus 2x plus 3 equals 0. So I'll do the quadratic formula. Negative 2 plus or minus the square root 2 squared minus 4 times 1 times 3 all over 2 times a. So I get 2 squared is 4 minus 4 times 1 times 3, so that would be 4 minus 12. So that's going to be an imaginary result. So this never happens. So the only critical number I get is x equals negative 1. So I'll put that on my little number line here. And then I will pick a value on this side of negative 1 and plug it in. So pick whatever you would like. And I get a negative, so it'd be decreasing. And then pick a number on this side of negative 1. And I'll pick whatever you'd like. I get a positive, so it would be increasing. So we change from decreasing to increasing, so that means my relative extrema is a minimum at negative 1. And then to find out what the y value is, I go plug in to my function. So I get the natural log of 1 minus 2 plus 3. So that would be the natural log of 2. I'm just going to leave it as the natural log of 2. If you want to find the decimal, you can find the decimal. And that would be my relative extrema. You can use the rest of the hour to work on homework, which is on page 330, problem numbers 45 to 78, every third one, 79, 80, 84, 87, 93, and 96.